Welcome back to the AI for Beginners video course. In this module, we are diving deep into how machine learning actually works. By the end of this video, you will understand the 3 fundamental ways a machine learns and how we measure the success of a trained model. In our previous module, we mapped out the AI landscape. Now we zoom in on the core of machine learning itself. We have a 5-part journey ahead, starting with the basics of what a model is, before exploring the 3 main learning paradigms: supervised, unsupervised, and reinforcement learning, and finally, how we test them. Let's start part 1 by building the vocabulary you need to make sense of everything else. Before we look at how machines learn, we need to understand exactly what they are building. What is a model, really? Think of it as the output of the training process, a mathematical structure that has captured patterns from data. Crucially, training is something we do once. But using that model to make a prediction, a process called inference, is what happens every time someone uses your system. An easy way to think about this is the student analogy. Training is like a student studying with flashcards. They see a question and the correct answer repeatedly until they can solve problems they've never encountered. The flashcards are your labeled data, the studying is the training, and the final exam represents your testing phase. To get there, we use features and labels. Features are the input information, like a house's square footage or location, and the label is the answer we want to predict, such as the sale price. These pairs are the essential building blocks for our models. There are 3 primary ways a machine can learn: supervised, which uses labeled examples; unsupervised, which finds structure without labels; and reinforcement learning, which learns through trial and error. We'll explore each of these in depth. Now let's begin part 2, supervised learning. This is the most common form of machine learning today, and it is likely that you interact with it daily without even realizing it. Supervised learning works by showing a model data where the correct answer is already known. The term supervised comes from the fact that the labels act as a guide, correcting the model's mistakes at every step of training. Supervised learning generally comes in 2 flavors: classification, where you predict a category like spam or not spam, and regression, where you predict a continuous number, such as the future price of a house or tomorrow's temperature. Let's look at an example of regression. If we want to predict house prices, our features are things like square footage and the number of bedrooms. Our label is the price. By training on thousands of past sales, the model learns the relationship between these features and price, allowing it to estimate values for new listings. For classification, consider spam filtering. Your features might be the sender and keywords. The label is simply spam or not spam. Unlike old-school filters that used handwritten rules, machine learning models learn the patterns of spam automatically. The actual training loop is simple but relentless. The model takes a feature, makes a guess at the label, compares that guess to the real answer to measure its error, makes a small adjustment, and repeats this cycle thousands of times across the entire dataset. We see supervised learning everywhere: in medical imaging, credit scoring, spam filters, and recommendation engines. In all these cases, success relies on having a high-quality, historically labeled dataset. However, the big catch is that creating these labels is often slow, expensive, and requires expert human input. This limitation is exactly why the other learning paradigms, which don't require labels, are so incredibly important. Moving on to part 3, we enter the world of unsupervised learning. Unlike the supervised approach, there are no labels and no correct answers provided. The goal here is simply to take a pile of data and find the hidden structure or patterns within it on our own. So what is unsupervised learning? Because there is no supervisor correcting every guess, the model explores the data independently to find patterns. While this makes it much cheaper to get started, it is also harder to predict exactly what the model will discover. The most common technique is clustering. The algorithm automatically groups similar data points based on their shared characteristics, without being told what those groups should be. It calculates mathematical similarity and sorts every example into a logical cluster. Consider a retailer analyzing customer purchase histories. By feeding raw transaction data into a clustering algorithm, the model might discover groups like frequent small shoppers or seasonal buyers, all on its own. These are patterns a human analyst might never have thought to look for. Another important flavor is anomaly detection. Instead of finding groups, the algorithm identifies data points that don't fit any normal pattern. This is vital for tasks like fraud or network intrusion detection, where the model flags unusual behavior without ever being explicitly shown a labeled example of fraud. Unsupervised learning appears in many places. Beyond customer segmentation and fraud detection, it is used for topic discovery in large sets of text documents and even for image compression by grouping similar pixel patterns together more efficiently. To compare, supervised learning is like following a map with a guide, while unsupervised learning is like exploring an unknown land. You choose supervised when you have labels and a known goal. You turn to unsupervised when you want to explore the data to see what patterns exist naturally. Welcome to part 4, reinforcement learning. This is perhaps the most exciting paradigm. Here, we don't use labeled examples or a static dataset. Instead, we have an agent that learns through a continuous loop of trial, error, and feedback. In reinforcement learning, an agent interacts with an environment. It takes actions, receives rewards or penalties, and learns over time which choices yield the best outcome. It is a distinct approach from the previous two, driven entirely by interaction and the pursuit of a reward. The core loop consists of an agent, an environment, and a reward. The agent performs an action, the environment responds with a reward signal and a new state, and this loop repeats millions of times until the agent learns the best strategy. A famous example is DeepMind's AlphaGo. Unlike older systems that used hand-tuned search, AlphaGo played millions of games against itself, learning to reinforce winning moves and discard losing ones. It discovered entirely new strategies on its own through this experience. Because these agents learn from scratch, they require an enormous number of attempts to succeed. This is why we usually train them inside fast digital simulations, where mistakes are free and we can run millions of training cycles in parallel. Reinforcement learning is the engine behind modern game-playing AI, advanced robotics, like teaching a machine to walk or grasp objects, and complex optimization systems, such as managing data center cooling or energy distribution. To recap, supervised learning needs labels for specific mappings. Unsupervised learning looks for hidden structures in raw data. Reinforcement learning relies on an agent interacting with an environment to learn through reward. Each has a distinct purpose based on the problem you are solving. Finally, we reach part 5. Now that we understand how these models learn, we need to discuss how we verify that they have actually learned a pattern, rather than just memorizing the data they were shown. Let's look at training, testing, and getting it right. Before training begins, we split our data into 2 piles. We use a training set to teach the model and hold back a separate test set that the model never sees during training. A common approach is an 80-20th split, meaning 80% of the data is for training and 20% is for testing. This is the only fair way to evaluate it. Why never test on training data? Think of a student who is given the exact exam questions to study beforehand. A perfect score wouldn't prove they understand the subject, only that they memorized the answers. Testing a model on data it has already seen has the same flaw. It masks real performance. This leads us to a critical concept: overfitting. This happens when a model memorizes the specific quirks and noise of its training set, rather than the underlying pattern. Like a student who memorizes practice answers but fails the moment a question is rephrased, an overfitted model performs poorly on new, unseen data. There is also the opposite failure mode: underfitting. This occurs when a model is simply too basic to capture the real patterns in the data. Just like a student who didn't study at all, an underfitted model fails on both the training data and the test data. Our goal is always to find the middle ground. How do we measure success? The simplest metric is accuracy, the percentage of test cases the model gets right. However, accuracy can be misleading, especially with rare outcomes. A model might look 99% accurate while failing to detect the one case that actually matters. Better evaluation tools are available, which we will explore as we progress. Here is a quick reference for the key terms we have covered in this module, including our 3 learning paradigms and the common pitfalls of overfitting and underfitting. Feel free to pause the video here if you would like to take a screenshot for your notes. To recap our journey, a model is a trained tool ready for inference. We use supervised learning for labeled mapping, unsupervised for finding structure in raw data, and reinforcement learning for trial and error optimization. Always split your data to avoid memorization, and look beyond basic accuracy to judge a model's true effectiveness. You have now mastered the fundamental ways machines learn. In our next module, we will go one step deeper to explore the technique behind most of today's AI advancements: the neural network. We'll look at how neurons and layers work together to process information. Congratulations on completing Module 5. You now have a solid foundation in how machines learn. We look forward to seeing you in Module 6, where we will dive into neurons, layers, and the training processes that power modern AI.